Alright, this is a project for Aerospace 497B, Experimental Methods and Projects. For this project we were working with the Google X Prize at Penn State, the Lunar Lion, and that is a project that is aimed to send a privately funded spacecraft to the moon and be able to transit 500 meters at the moon, as well as taking data of video and images and sending it back in near real time. But in order to be able to complete the objective, the Lunar Lion has to be able to land on the moon. And one of the problems that could happen would be if it came in too fast on the moon and flipped. That is what this project aimed to look for, the velocity and angles at which the Lunar Lion would flip and not be able to complete its mission. In order to do this, we used a scale model of the Lunar Lion, as you can see here. And we have the model that we used in the tests. It was about 1/6 the size of the actual model, so it had a diameter of 7.188 inches, a height of 2.59 inches, and the feet were 0.5 inches, and the mass was 0.48 inches, 0.48 kilograms. And it was made out of PVC, and it was used as scale to scale the length. We used a scale. We multiplied the original model that we had by 0.14, and we multiplied the mass by 0.14 cubed.
The apparatus that we used to test our project was a tracking cart system, and this both were designed simultaneously in conjunction together. We designed the cart with a couple of key ideas. We wanted it to be able to pretty much just carry our model down easily and smoothly. We had some different ideas of how we wanted to do it, but we ultimately ended up with hanging a bar off the side so the track would not interfere with the model at all when it came down. And we used string to actually attach it because we wanted a design that once it hits the bottom, the model would be free to do whatever it wants and wouldn't have any constrictions by the cart itself. So lightweight string was the way we used. And the lightweight string also gave us freedom to adjust the model angle, so it could go like this or like this for different runs. One of the bigger concerns was once we got to higher angles of attack for the track, that the cart would have a tendency to flip over. So we went with like a roller coaster design where the wheels would encase the entire length of the track. There's one set on the bottom and one set up on the top. You can see that on the left image there. The track gave us it's there for the cart to go down firstly, and secondly it can also be adjusted by angling or moving the brace back and forward along the bottom stabilizer, and that gave us the freedom to test many angles of attack as we wanted to. We used a basic energy balance equation to scale our velocities and get some estimations of what velocities that we're looking for when we actually did the testing. We reduced it, and we can govern the velocity at the bottom of the track when the model impacts by doing one of two things: changing the counterweight mass or changing the length along the track at which we start.
One of the goals of this project was to figure out the tolerable speed that the lunar lion could land at horizontally, and that was calculated simply by using the square root of the scaling factor and multiplying it by the speed of the model.
The sand bed that we used was, we did a whole bunch of research on soil simulates, but we decided, since there are other constraints within this project, that simple play sand would do. And we decided that we wanted, for the ideal condition, the lunar lion would land on a perfectly sandy surface that's deep enough that no bedrock would have any interference with it. So we're just working with perfect sand. So for our model, we used a sand bed that was about 1 inch in depth, which is half of the height of the model. So so that's significant enough that we don't have to worry about any bedrock interactions. The experimental procedure was designed to make efficient use of time. It was designed to minimize the changing of the track angle, because that took the largest amount of time. So we would run every test at one angle, and then we would change the angle. And that's pretty much what that is. And we did that for about 100 iterations.
Once all of the runs were completed, we looked at the videos frame by frame as soon as the lunar lion model comes in for a landing. And from this we were able to determine the speed and the angle of attack that it came down at. And that was done by using this ruler in the background, which is graded in centimeters. And since the camera took pictures at 32 frames per second, we were able to use that and the distance that it traveled to calculate the speed. And once that was done, we could scale that up to what that speed would be on the lunar lion itself. And also, we were able to use trigonometric properties to split that speed up into horizontal speed and vertical speed. And we also calculated the angles of attack simply by drawing a line as best as we could through the model itself and calculating that angle using a protractor.
Do you want me to show part of the video? Oh, did you close out? Where's this?
The video simply shows all the runs one by one, and the examples where the model came down and lifted up at all are shown once again in slow motion.
So we'll just show one or two of these. Is this the right one? Yeah, it is.
And originally we had planned on using that if the model came down, landed and flipped, that would be a failure. But since that never happened, we looked back at the video and decided that any time the model comes down and the rear end lifts up at all, we would consider that a failure, since that can be looked into more in the future. And there was actually a surprising amount of times that the model came down and lifted up. I believe it happened 13 out of the 100 times that we did it. In the future, I think there are many improvements that could be made on this design. You could use lighter weight material to demonstrate the lower gravity that's experienced on the moon. You could also try to figure out a way to keep the angles of attack relatively the same for each run, because what we found was that once this begins to move, the cart moves first and then drags this behind, and it swings backwards and comes in a lot of times at a negative angle of attack or really close to zero.
Yeah.
The Lunar Lion is a really ambitious project, and a successful landing is critical to its operation. In this class, it was really helpful to have experience in designing a project. We worked with a very broad question. We did research on it, we designed an experiment, we fabricated all of the materials that we would need, ran the tests, and analyzed the data. And what we found was that for future research, the things to improve would be to get higher horizontal speeds and use angle of attacks that were close to zero, because what we found was that when it lands close to zero, the front leg catches on the sand, and that provides a tipping point for the model to go about, where originally I believed that it would come down at a higher angle of attack, land, and bounce up, but that seemed to aid it in catching the back legs and pulling it towards the ground.